video, we'll be talking about retrosynthesis. And this is planning a synthesis backwards by starting at the product, i.e. the target material, and taking it back a step at a time to a more simpler precursors. Backwards requires rather good problem-solving skills and a good knowledge of organic reactions. And so if you look at this strategy, realize that starting materials with reagents is forward thinking. So that's quite simple and students are quite happy with that. At the same time, starting materials, getting to a target material and trying to figure out the reagents, a bit puzzling, but it's okay. On the other hand, if we got a target and we're given a reagent, but no starting material, then we got to think a bit backwards, and that's quite annoying for some students. In this work, we'll have target materials, and we got to think about starting materials and reagents, and of course, there is no help here, and so it is quite demanding. To solve this dilemma, we need to learn some new terms and develop some key strategies. For example, starting with this alcohol, the question arises, how can we synthesize it from simple precursors? Well, we can make a disconnect notified by this line, this curvy line. It is an analytical operation which strategically breaks this bond as possible starting material. So it's the reverse of a synthetic operation. Realize that I've broken it into two simple components, a cyclohexyl ring and an E-file. We then can generate synthons. Now note that here we have a retrosynthetic step, and this arrow is a retrosynthetic arrow, meaning that the species our target was made from. These synthons are idealized fragments resulting from the disconnection, and it's usually a result of breaking carbon-carbon halide bonds, and generally they have imaginary charges. Now, from the synthons we can generate actual synthetic equivalents. And so herein you can see we have a Grignard with a ketone. The synthetic equivalent delivers sources for the synthons. And so we can have a forward reaction like this. You recognize that this is a carbonyl with a Grignard followed by an acidic quench. Retrosynthetic analysis, we could ask quite a few questions to aid us. For example, is there a change in the carbon skeleton? Is there a change in functional group? This is functional group interconversions. So if there was a change in the carbon skeleton, it most likely came from a type of coupling reaction, say for example a Wittig, or a cleavage reaction, say for example ozonolysis of an alkene. Sometimes the disconnection does not to our starting material, and a functional group conversion is desired. Herein, we can see that in this first material, we can have a disconnect, which occurs here at this carbon-carbon bond, i.e. a coupling. We could put it down to a still coupling, and so these would be our starting material. You can see here, for example, another disconnect. Here is a new carbon-carbon double bond, and we could have a Wittig reaction that was involved. In this case, you can see that we have an ester, and this could have been a cleavage reaction where there was an oxygen insertion from this peroxycarboxylic acid. Herein, we have a table showing some simple transformations that you should be familiar with. So you should be able at this stage of your career to move up and down a column by using various reagents and synthetic techniques. And we can move from left to right, knowing that there's an increase in oxidation level. And so to move from, say, for example, an alcohol to a ketone, which is an oxidation, you would require something like a PCC or a chromate. And then, of course, you can see that if we had a primary alcohol, we could drive it all the way to the acid, that sort of thing. And you could go from right to left. Again, you can see that we're reducing the oxidation level. And so there's various reductions that are occurring. You can see that on the right-hand side, the extreme right column, we have quite a few carboxylic acid derivatives, and that's predominantly nucleophilic substitution reactions. And you should be familiar with that as well. And the reason why we focus so much here on carbonyls is because we know they're terribly important in organic chemistry. Functional group interconversion, we usually represent this with a retrosynthetic arrow with FGI above it. Now note, say for example, you're quite familiar with some of these guys because these are based on some of the aromatic chemistry that you've done in the past. Say for example, you can reduce a nitro group to an amine, say for example using tin HCl. Here, for example, we can use a strong oxidant to convert a benzyl carbon to an acid, hydrolysis of a nitrile, and of course, conversion of the nitrile into an amide. We also have reduction of the nitrile to give primary amines, or reduction of the azo group to give you the pure primary amine. If you look further, for example, having an imine will give you a secondary amine. And of course, you can see here that we have here a tertiary amide. Could have a tertiary amide reduction, say, for example, with lithium aluminum hydride would generate this tertiary amine. And here you can see that we can also oxidize a primary alcohol to an acid, or oxidize, as we saw previously, a secondary alcohol to a ketone, or a primary alcohol to a aldehyde, say for example using PCC. And we are familiar with diols, transdiols, when we worked in the past with our elementary organic chemistry. Note that all of these are basically redox reactions, or sometimes some hydrolysis. Throughout the course, we'll come across simple synthons, and we need to be familiar with this synthetic equivalent. So herein, an alkyl cation could be generated from an alkyl halide or a tosylate. An aryl cation could be generated from an aryl halide or an azo species. Oxomethyl lithium, we have the synthetic equivalents. And oxoalkylium, we could easily use, say, for example, the amide as we saw before, or an ester, and so on. For example, if we have an acid, we could easily use a Grignard carbon dioxide quench, that sort of thing. For synthon like this fella here, then of course you recognize that as a species that generated from an epoxide. We could have a species like this, which is generated from the enone type species, where we have the positive electrophilic center at the beta carbon. Or nitrile would have an unsaturated species like this, and so on. These are positively charged synthons, and therefore we will need electrophilic species to work with to give us the synthetic equivalent. Negatively charged species, synthons, then of course we're going to be looking for files. And here, for example, if we're looking at an alkyl anion, then we could use, say, a Gilman's or a Grignard. An aryl anion, same sort of thing. We could even use, say, a Borwein, for example, in the steel coupling. Alkynyl anion, then you're looking at a vinylic species, for example. Acetylide, we can start off with a metal acetylide species. The cyanide, and then of course we can use the salt. If you have an alpha carbon that's negatively charged, then of course we're looking at enolate chemistry, including our beta esters. Herein we're looking at a nitro with a negative charge at the alpha carbon, and then of course our synthetic equivalent will be our nitro, our alkyl nitro. And there's a host of ylides that we can use. For example, we can see the Wittig reagent. We can see a species here, the phosphate for the on-emmons, and so on. We are familiar with our synthons and synthetic equivalents and terms used in retrosynthesis. We should go ahead and try to analyze our species and try to do a synthesis. And remind yourself that the analysis is recognizing the functional groups in the target material and disconnect around that region. Repeat is necessary to find the most available starting material. And in your synthesis, you want to write out a plan, adding reagent and conditions, and modify that plan according to the most efficient route that you can find in the lab. Start off with this simple ether. We can see that disconnection could be either in this region to give us those synthons, or in this region to give us those synthons. Now, if you're looking at an ether, we know that a primary way to get around ethers is the Williams ether synthesis. Now, realize this, it'd be rather difficult having an alkoxide attacking, say, a aryl halide. So this route is really rather poor. And so this will be a more acceptable route. And so we can easily come up with a forward synthesis where we have the phenol reacting with our alkyl halide to produce our target material. Let's get the retrosynthetic analysis for the following three compounds. We're going to pay special attention to the relationship between the functional groups. Note, for the one on the left here, we have unsaturation between the alpha and the beta carbon. Now, we are looking at either an aldol condensation or a simple Wittig. But because of this acidic proton, then these reactions would not be pleasant. And so what we need to do is have a functional group interconversion from an ester This makes it quite simple now because the disconnect here realizes these synthons. And if you note with these synthons, they're quite familiar with you because you can see that we can have an aldehyde with a Wittig reagent, and that will give us our coupling reaction. So in the second case, there is no simple enolate disconnection. So we got to think a bit more farther afield. And herein we're looking at a functional group interconversion from a nitrile. And so we can easily have an alkyl, an allyl halide with the cyanide as our starting material. In the third case, it takes a bit of strategy, but we can see that again we have this acidic proton, so it's best to convert to an ester. Herein, we can now have this disconnection. And if you remember, I want you to consult the chart that we gave you on these type of synthons. So we have here an allylic cation, which we can generate from an allyl halide. And of course, we have an anion on an alpha carbon of an ester. And so immediately what comes to mind is the malonic ester synth. So what we have is alkylation of the malonic ester. In your retrosynthesis, there's a few pitfalls that you have to avoid. And so in this first case, we want to avoid chemoselective issues. If we look at this fellow and we disconnect here, then of course this route gives us these two synthons which we can generate from an enolate of acetone and that of an acyl halide. This would produce a diketone, a beta diketone to be exact, and then we'd have to selectively reduce this ketone on the left to the alcohol. This is chemoselective reduction, and it's rather difficult, so it's something that we need to avoid. A preferable route is to disconnect in this region. These are our possible synthons, and if you note, we could have an enolate with this ethanaldehyde to generate our product. So we treat this acetophenone with LDA to give us an enolate, which we then can attack our ethanaldehyde with a quench will give us our desired product. And another pitfall to avoid, and this is regioselectivity issues. So we can disconnect in this region from this simple ether, and we can see that we have an alkoxide with some sort of allyl halide. But realize this, that we have to regioselectively deprotonate this alcohol over this lot, and that's virtually impossible. With this route, however, we can generate these two synthons, and the alkoxide in this case is a fairly simple species to form. And of course, this synthon here, you should recognize, is from an epoxide. And so your forward reaction would look like this. Alkoxide with your epoxide to give you the desired product. Of course, there's a quench involved. Remind yourself that the alkoxide attacks at the least substituted carbon of the epoxide because it's a base attack. condensed lecture was suffice and it worked for you, please go ahead, like and subscribe, and we'll bring you more content in the near future.